I'm expecting something good to happen today. Hello everyone, it's June 27th. Yesterday was a disaster, but today I have a clearer mind. Hopefully I can do things a bit better. I mean the good thing is we have two snippets, right? One is for union find and the other is for the binary index tree. So with these two, hopefully I will not be scared if a question requires union find or it requires segment tree. All right, let's take a look. I have 7 here. Damn, that's a lot. I don't think anything is related to me. All right, let's take a look what we have today. Today's topic, today's question is very simple in its title. Just one word, candy. All right, candy. There are n children standing in a line. Each child is assigned a rating value given in the integer array ratings. You are giving candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. What do you mean, than their neighbors? Candies than their neighbors. Higher ratings than their neighbors, then they can get more candies. What do you mean by higher rating? Higher rating than what? Than their neighbor, most likely than their neighbors. Return the minimum number of candies you need to have to distribute the candies to children. Okay, let's take a look at the examples. We have 102, so that means the first kid needs to have more candy than the second kid, and the third kid needs to have more candies than the second. Probably no. It's just the neighbors. So the third kid has 2 ratings. The first kid has 1 rating, but because the first kid is not a neighbor of the third kid, so the third kid does not have to have more candies than the first kid. Okay, that's all right. First, second, third has 2, 1, 2. Okay, so this thing, so this kid has to have less than this kid, and these two have the same. 1. Oh, it doesn't matter. A third kid has 1 candy because it satisfies the above 2 conditions. Each child must have at least 1 candy and higher rating. So this one has the same rating as this, so this doesn't have to have the same candies as this. So it's 1, 2, 1. Okay. Ratings, numbers. All right, these innocent-looking questions, always not innocent when you solve it. Okay, let's see. So everyone at least have 1 candies, all right? And then we just need to find out who needs to have more. Apparently, if we have we start from the first one, right? And then the first one has 1 neighbor. And then if the first one's neighbor, if first one's rating is larger than the neighbor, then this one must be 2, right? And now we go to here. Oh, and this is the problem. If the second one, like if we have a rating 3, 2, 1, if we have ratings 3, 2, 1, I think that can illustrate my problem. 3, 2, 1. So we say everybody get 1, and 3 is larger than this, and a 3 needs to get, no, the first kid needs to get a 2, right? And the second kid is 1, third kid is 1. And the second kid, it looks to the right. Oh, I'm more than this. So I need to get 2. Then the first one needs to get 3. So this has to be 3, 2, 1, right? So that's 6. I think that's 6. We got 6? Yeah, that's 6. Okay. So go higher to lower is not going to work. So we have to go low to high, which is true because if I am the lowest, if I have the lowest rating, then I only get 1 candy. And everybody has lowest rating gets 1 candy. And so what we look for the lowest one, and we assign it to 1 candy, and then we look at its neighbors, right? And the neighbors, hold on, if I have the lowest rating, then my neighbors must have either the same rating as me or higher rating. If they have the same rating as me, then they're also the lowest, so they get 1 candy. And if they have higher rating than me, right? If they have higher ratings than me, then they're the neighbor, so they should have a higher number of candies. So they should have 2 candies, right? They should have 2 candies. Okay, so we set them to 2 candies, and then what? We look for I want to start a random list of numbers, just kind of to test out the theory, right? So give me a random string of numbers. Okay, so we're gonna say what random, let's say 1 to 10. All right, give me 5 numbers. All right, this is 5 numbers. So we have 10, 8, 5, 10, 8. Oh, then we can actually reduce this. If everybody minus the smallest, we can actually reduce it to, oh yeah, the values is actually, we can reduce to 1. So if we reduce it, everything minus 4. It'll be easier for me to think about. So it's minus 4, that's what it looks like, right? Okay, no, that's 4. Minus 4, that's 4. No, did it wrong. This is 4, or minus 4. Okay, so we have 6, 4, 1, 6, 4, right? 6, 4, 1, 6, 4. If I say the smallest getting 1, and then its neighbor, the smallest neighbor getting 2 candies, because they do not have if I am the neighbor of the smallest has to be 1. If I am the neighbor of the small, do I have to be 2, or do I have to be something more than 2? It depends, right? It depends. If I am neighbor to the smallest and the second smallest, and the second smallest has to be, I can think of a scenario, right, that like this. If it's in this scenario, 1, 3, 2, 1, right? 1, 3, 2, 1. Then we know 3, 2, 1 has to be the way it is. 3, 2, 1, and this is a 1. Right? This one is going to be 7, which means the neighbor of a small of the lowest is not necessarily 2. It just can be 3. Okay. That's not working. Dynamic programming is to say, if we say, I'm looking at this one, right? I want to know how many candies this one need to do. So I say I'm going to solve this problem, solve the remaining problem. If the remaining problem has been solved, then I know what this one needs to give. It depends on this and the number of candies this one has. If this is larger than me, then I must be 1. If it is smaller than me, I must be 1 larger than this. If it's equal than me, then I'm 1. Okay, that's fine. So now we look at the rest. We say, is the count of this affected by this? No, I don't think it's affected. Maybe recursion can work. All right, let's think about it one more time. I say, for any candy, right? For any candy, for any children, for any child, how many candies I am going to receive is dependent on the remaining. Right? If we solve the remaining, if the remaining give me the minimum arrangement, then I will have the minimum arrangement as well. Does that make sense? I'm not sure. I'm not sure about the minimum. But it does make sense. I mean, we know the edge, right? Actually, we can actually go from front. We know the edge, right? The edge has to be determined because I only have one neighbor, right? If my neighbor is bigger than me, I'm guaranteed to be 1. If my neighbor is larger or equal to me, I'm guaranteed to be 1. So in this case, I know this must be 1, and this must be 1, and this can be determined by this. What if I'm larger? So if I'm smaller, I'm good. If I'm larger, if I'm a large value here, then I'm dependent on the smaller one. Then we can defer, right? If I am a large value, then I'm going to defer to the smaller one. So I don't consider, I don't consider, so I look to this one, right? I look to this one. And this one, if this is smaller than the next one, or smaller than equal to, then this must be 1, right? Because the one in front of it is bigger, and I don't care about anything that's bigger than me. I only care about something that's smaller than me. And then I have something that's bigger than me, right? If I'm like, this is bigger, and this is also bigger, then I know I must be 1. Like I can take 1. That means I can take 1 that will not violate anything. Okay, so basically go from the front, right? Going from the front, what we're saying is if it's larger than the remaining, then we defer. If it's smaller than the remaining, we set it to 1. Okay, if we set it to 1, and then going for the next one we'll have to set it to 2 at least, right? So 2 at least. And this thing will have to also check. If I am smaller than my next one, then I'm 2. But if I'm larger than the next one, then I don't know. But I have a base. The base is 2. So I defer again to the rest. And that might work. That might actually work. And we run recursion for the rest, and the rest will give me the value. And if my neighbor to the right is larger than me, then I have certainty of value. I have certainty of value. If my neighbor to the right is smaller than me, then I don't know what to do. I am going to defer until I find out my neighbor, and then I can get my value. Okay, I think this might work. Yeah, this might work, but can we do it like without recursion? If this is smaller, if this is big, and this is small, I probably have to do it. Let me try. I have this idea. Let's see if it works. So let's give it a shot. Oh, my laptop is a bit slow today. It's screaming right now. Okay, so here's the idea. The idea is helper, right? So we're gonna have an index, and it's the result. No, not result. Candies. Candies is going to be nobody has any candies initially. Land ratings, right? So this one is not going to return anything. So what we do is go to the first index, and we say, we always compare to the right neighbor, right? We say if we actually add another, we add a dummy. If I add a dummy, that'll make it a little bit easier to handle. So like we say we look to the right, and if the right is larger than me, then I'll set myself to 1. Actually, it's not set myself to 1. If the right is larger than me, I'm going to add 1 candy. If the one to the right is not, if the to the right is smaller than me, then I'm going to call the right. After it's done, I'm going to check what the right candy is. Okay, so index will keep going until, so the end is index equals, let's give n equals land ratings, right, and then it's going to be n. So we say if this equals -1, then I'm the last one, right, I'm the last one. Then I have situation I cannot compare to the right. If I cannot compare to the right, what ratings do I have? What candies do I have? If I cannot compare to the right, then I need to check yeah, that's the question. If I cannot compare to the right, what candy should I have? I mean, it depends, right? If my left, now I'm going to talk about if my left. If my left is larger than me, then I can safely do 1. If my left is smaller than me, then I do not know. If my left is smaller than me, then my left is smaller. No, this does not work. If my left is smaller than me, and we are going to the end, right? If we're going to the end, and my left is smaller than me, then we have the same trouble. I cannot run. If my left is, wait, hold a second. If my left is smaller than me, then my left should have got a result already. Because we say if the left is smaller, if I am smaller than my right, then I shall be able to have a value. And if I am larger than to the right, then I don't have a value because I need to wait. If I'm smaller, then I can have a value. If I'm smaller, I can have a value. So we always have to look to the left as well. So what do we say? So everyone come out. If I am smaller than the left, and I am smaller than the right, then I can be 1. If I am smaller to the left, and I'm smaller to the left, but I'm bigger to the right, I do not know. If I am larger to the left, then at least I need to be one larger than my left. And I also don't know. And then I have to keep looking. And if I am smaller than the right, then I'm set. And if I am larger than the right, then I still don't know. So yeah, I think this is, right? This is. So I say, if I'm going to the end, then I'm going to look, right? So we say um, if ratings, basically it's n minus 2, well, what if we only have 1? There's no n minus 2. Oh, we can add, let's say we add something giant on both sides. Right, we add something giant on both sides, which means, yeah, let's add something giant. Yeah, it happens every single time. Come on. Oh, come on. It's struggling. All right, I think we're back. All right, so we have this. N is equals to this. If n is like this, then the values will be slightly different when we want to check for ratings. So our index is going to be the original index now that we are expanding ratings. Yeah, it's oh man. We'll start from 0 to this, and then actually just plus 1, right? So the ratings, index is this. So index, oh man, this is, it actually has to be n, right? So we index, when we start from 1 to n, right? 1 to n. Index start from 1 until n. So we say if ratings index minus 1, right? If index minus 1 is my left is if my left rating is larger than me, larger or equal to ratings index, then Candy's index, oh man, this one has to change as well. Naturally, we don't need, we just need one side, that's fine. Then Candy's index plus equal 1. Alright, that means if my left is bigger than me when I go to the end, then I'm certain that I only need one candy. Else, right, if my left is smaller than me, then we say Candy's index plus equal Candy's index plus equal or equal. It's actually equal. Actually, we can say equal 1, because this case equals Candy's index minus 1 plus 1, right? Because I have to be 1 larger than whatever this one gets. So that's the end condition. And so else, if we haven't reached the end, then we say we want to compare, right? We want to compare myself. So the same thing. If I say if ratings index minus 1, if I am smaller, no, if I am smaller or equal, right? If I'm smaller or equal to the next one, index plus 1. If I'm smaller or equal to the next one, then my ratings, my candies, shall be equals my previous candies. Hold on. If I am smaller or equal, right, than my candies, it depends on my previous, so it depends, actually it depends. So if I'm smaller than my next, then if my ratings is also smaller, if my rating is smaller or equal, right, if my rating is smaller also equal to ratings index minus 1 from the previous ratings, then I say my candies is going to be 1. Else, my candies is going to be candies index minus 1 plus 1. Else, if my rating is larger than my next rating that I do not know, then I have to go helper, right? Helper index plus 1. And after that, then we check, right? After that, then we check. Because I already know I am bigger than the next one. Right? I am bigger than the next one. So after it's done, I need to check my next one, how much it is. So I need to increment. And I need to also check to the front. So we still have two checks. We say if ratings index, if I am smaller or equal to my previous one, right, if I'm smaller or equal to my previous one, then my candies index will equal to candies index plus 1 plus 1. Else, and my candies index will equals the max of candies. That means I am larger than both on both sides. So index minus 1 and candies index plus 1 plus 1. Right? And not sure. I say helper. When I start with helper, candy is going to be start from 0. No, we start from 1. We start from 1. And we run helper. After that, we're going to return. We're actually going to print. Let's print candies as well. And we return some candies. Alright, let's try this. So our first test case is 1, 0, 2. This one shall return 5. Second test, 1, 3, 2, 1, return 7. So we're going to do ratings. And this one will be candy ratings. Nope, not correct at all. Oh, the last one. I have an issue with the last one. Hold on, why would I have an issue with the last one? Why would the last one be 0? That is interesting. The last one is 0. Okay, let's go back to this. Print out 2, 1, 0. So I have 4, that's correct. And then we have math index front. And then index equals n. N is the original length of ratings. So index equals n. We say if ratings, also probably print ratings as well, right? Print ratings, inf, right? So if this is larger than this, if I'm larger than you, Now, if this is larger than me, if not, then I shall equal to this plus 1. Let's print out let's print out the ratings, candies at the end. So let's not print out here. Let's print out here. So this is the candies at the end of each one. So that's the first run. So we start helper 1, right? Helper 1, then 1 is not equal to n, so ratings 1, 0, 1 here. Ratings 1 is smaller than this, no. Ratings 1 is larger, so we do helper 2. Helper 2 comes in, 2 is not equal to n. Over here, we say ratings this, right, is smaller than this, yes. And we check if this one is smaller to this, yes. So we set candies this equals 1, right? So this one set to 1. Oh, I never visited the other. We only start going here. Huh. Ah, that is the problem. So I think what we need to do is, if this, I set candies, and then I need to go. Else, I go first, then I set the candy. So I think if we, after we set it, then we go. Then this one we pass. So let me comment out this and comment out this. So this one we pass. How about the others? Now we all pass. All right, try our luck. Let's try our luck. Yeah, I'm gonna try a few more. For example, this case, I only have 1. Okay, 1 pass. Let me just do some random numbers. Actually, it's not random, just me smashing the keyboard. Let's see what's gonna happen. Okay, this one pass. Try one more time. All right, let's try a big value, like oh man, I'm having internet issue again. This thing is very, very troublesome. Anyway, let's try here the same thing. All right, let's try like a 10,000. Ooh, it's gonna take a while to render 10,000. So I'm gonna copy this whole thing. 10,000 values. Let's try it. How long it's gonna take to run this? I have some confidence now. Maybe that is the way to go. All right, let's try submit it. Pending, judging. Oh, we got it. Huh. Did we get lucky on this one? How should I express my my thought process? Wait, what is this a medium question? Okay, first let's see the runtime. I think the runtime is ON because there's no backtracking, no nothing. We just straight through. Let's see the good solutions. Is yeah, I don't see any recursion. Yeah, there's no recursion. I think the good solution doesn't require recursion. Let's go to problems. Maybe it's not just a medium question. Huh, it is considered a hard question. You know, this is the thing that I don't understand, right? Some days I'm in a good state and the problem like this doesn't feel like a hard question to me. But someday, like yesterday, was just so hard. Oh my God, can't even explain. All right, so let's write down what our thought process. Okay, so here is my thought process. I feel very lucky that we solved. I feel very lucky that we solved this problem in fairly short period of time. I mean, about half an hour. My thought process is like this. For any child, for any child, I just saw his or her rating situations there are four. Right? There are four conditions, four situations for his or her rating. One is large, for his rating relative to the two neighbors on the left and right. So one is large, small, large. No, let's not do this. Say left is larger equal to current is what do we say? Smaller equal to, right? And then smaller equal to I should say large and smaller equal to. Smaller equal to right. And left is large to current, and current is large to right. Left is